Hey guys, welcome to this course on RISC-V processor design. My name is Marco and I'll be your instructor. I hold a PhD in electrical engineering. My research focus has been mostly computer architecture and digital design. I've got 6+ years of teaching experience at both undergrad and grad level on RISC-V, and I got 10+ years experience in the RISC-V industry. I started in September 2016, mostly working on stream data processing accelerators, which is a real fancy word for saying AI accelerators and network packet processing at 100 gigabit plus. So what we will learn in this course is the design and implementation of a RISC-V processor. We'll go into the details of what kind of processor this is, but for now, just so you know, it's a very small processor that will allow us to see 90% of computer architecture concepts. There are no prerequisites to this course. It's targeted to people straight out of high school. I want to start off with a huge disclaimer by saying that the verbiage in this course is not meant to be a comprehensive guide to RISC-V or processor design. While this course is more intended to give you a quick and fast track to building a RISC-V processor from the ground up. So what is a processor? And a processor is a device that executes instructions upon data. You can think of it as the brain of the computer, and we describe the microarchitecture, so how it works, in a hardware description language. There are many hardware description languages like Verilog, VHDL, System Verilog, and the one that we're going to use in this course is System Verilog. It's very similar to C. We will go over everything that we need to achieve our goal in the coming lectures, but just so you know, we are not going to dive deep into the System Verilog. There's no need for that. There's no real advantage in knowing everything there's out there on System Verilog. We will cover all the stuff that we need to get the job done. When talking about processors, we want to know what the processor is capable of, how it's organized internally, and all this kind of stuff. And the capability of a processor, and most often a family of processor, are defined in what is called the instruction set architecture. And the instruction set architecture is the single most important document. So it's a document that you can have for a processor or a family of processors, and basically describes the instruction that the processor can execute, how the registers, which is the internal storage facility of the processor, how those registers are organized, and how to move data around those registers and in and out of those registers. So how the processor interfaces with memory, if there are special purpose registers inside the processor. So it basically details everything there's need to know about our design. So what is RISC-V? RISC-V is an open source instruction set architecture. It was created at UC Berkeley in 2010, and it has a lot of desirable features from an instruction set architecture point of view. And the reason why it's gaining a lot of traction is because it's open source, it's extremely simple, which makes a good platform for teaching. It is flexible, and it has a huge and growing ecosystem in terms of industry partners, tools and resources, and active community. Just think about this course. Jumping into action mode, what kind of tools we will use? I've already said that we're going to stick to System Verilog for our hardware description language. We're going to use verilator for fast hardware simulation. The output of this verilator is going to be most likely a waveform file, where we will basically see all the signals going up and down in our system, and those signals can be visualized with a waveform viewer, which is called GTK Wave. Again, this is all the software here is free and open source. We're gonna go over the steps of setting up this software in a second. In terms of development environment, we're gonna use VS Code or whatever you want to use for writing code. I personally use Cursor, which is a derivative of VS Code, and we're gonna use Git for our version control. To start working with RISC-V, we're gonna use mostly two open source software. That is the RISC-V new toolchain, which is basically an open source compiler for RISC-V. The Whisper instruction set simulator is a piece of software that you feed a RISC-V program, a RISC-V object file, and it executes. And we're gonna use this output of this instruction set simulator to compare the results of our hardware, of our core, and make sure that everything is nice, everything matches, so we don't have any errors in our design. The course structure is extremely simple. We're gonna go over the RISC-V ISA basics, and even before that, we're gonna lay the groundwork for everything that we need to know, like logic gates, sequential systems, system Verilog, and all the stuff that we need to know to gather and study and design a RISC-V processor. We're gonna go over a single cycle CPU design, the pipelining fundamentals. We'll start building these tiny betas. Then we're gonna go over testing and verification. So how do we know that this processor is actually performing what it's meant to perform? After that, we're gonna go over a few tricks to optimize the performance, and that's pretty much it. Before setting up the development environment, what I want you to do right now is to click on this link, which you will find also in the comment section below or somewhere here. If you click here, you will land on this web page, and what this web page does, it collects your email so I can invite you to our Git repository. Well, you will find these slides, all the course material, like a solution to exercises, additional material, handouts, whatever we will cover in this lecture is going to be uploaded on that code base. So make sure you have access to it. And what's gonna happen, you put your name, you put your email, you click, you wait. Two emails. The first one is a welcome email from me, and the other one is a GitLab invitation. Make sure to accept the invite by clicking on join now, because this invite, it's gone in 72 hours. If you don't sign up in 72 hours, you have to email, and we have to do this all over again. So you click on join now. That's pretty much it. Let's jump into setting up our development environment. And for this course, we're gonna assume that you're running a Linux machine, because this is the most common setup you're gonna face whenever you start working in this industry, and that you got access to the code base that we saw in the previous step. You can easily replicate all those steps on macOS and Windows, but we're gonna use Linux throughout this course. So let's start with the following tools: VS Code, verilator, and GTK Wave. So VS Code is extremely easy. You just type Visual Studio Code on Google and you download whatever distribution you have for the operating system you're running. Once you install Visual Studio Code or any derivative like Cursor, you should see something like this. Okay, this is the source code for these slides that you're seeing. So here you have a file navigator, here you have the source code analyzer, and you can even pop up a terminal. So we're gonna use extensively the terminal function of Visual Studio Code. Now that we installed the editor, we can start going ahead and install verilator and GTK Wave. And for this part, I have to switch to the machine that will run Linux, and it's here. So this machine is running the latest version of Ubuntu, at least the latest long-term supported one. It has a 16-core CPU with 32 gigabytes of RAM. You can get away with much less than this thing. As a matter of fact, this thing is a mini PC, so it's not that powerful. So now we can go ahead and install the first thing that we need, which is verilator. If you look inside the packages of Ubuntu, there is a verilator, but it's an extremely old version. Most of the stuff that we need for system Verilog to work in verilator will need a much more recent version. So what we're gonna do is we're gonna compile verilator from scratch. Don't worry about that, I'll guide you through it. So let's search for the verilator repository, which is hosted on GitHub. Let's go here. This is the repository for verilator. Let's go here in releases, and as of shooting this video, the latest release is 5.32, so let's go with that. Let's right click on the targz file and let's copy the link address. Now in the terminal, the Linux terminal, let's get this thing downloaded. We wget and let's wait for it to finish. Okay, it's done. Let's expand the archive. And let's see what is it here. There should be a verilator installation. We're going to run a few commands. So the first command that they want to run is autoconf. Okay, if it's not installed, so this is a fresh installation of Ubuntu, so I'm going to face a lot of the same issues that you guys are facing. So let's install autoconf. Okay, let's run it again. Okay, so this command completed successfully. Let's see what we need to do. Configure. Okay, so it's failing with no acceptable C compiler found in path, meaning that we don't have a C compiler. Ubuntu has a real nice package called Build Essentials that contains everything we need to have in order to compile C programs. So let's go and install that. Let's go, yes. Let's give it a minute. Okay, let's rerun configure. Cannot find Flex. Let's install it. Okay, let's install Bison. We made it past the first few errors. Now we're ready to compile verilator. So what we want to do is type make -j. If you're on a multi-core system, which I assume, let's type this thing to allow make to fully leverage all the cores in our system. Okay, it took me like 5 minutes on my system. I don't expect it to take more than like 10-15 minutes on slower systems. Now the last step is to make sure we can execute verilator. Do so by typing sudo make install. There's a small error here that says help to mon, so let's install it. Yep. Let's do it again. Perfect. So now we have the executable for verilator in user local bin verilator. And let's do a quick test. Let's type this into the terminal and let's see what we get. We get an output that says verilator 5.32, which is the one we downloaded. 1st January 25, unknown rep. I'm sure that's a bug on their end. But we installed verilator successfully. Now The last step is to install GTK Wave. And for this one, we can use the package that is supplied with Ubuntu, GTK Wave. That's it. On the next lecture, we're gonna put everything together in terms of starting to write some system Verilog, simulating it with verilator, and starting to see some waveforms and start to get some intuition about how the different building blocks of a processor work. All right, I'll see you on the next episode.